Hello again. In this last set of slides for this quarter, I talk about LISA for binary variables. So far, we have dealt only with continuous variables, and now we switch to the case where the observations are 0 and 1. And in those instances, the classic test for spatial autocorrelation is called a join count test. Not joint counts, but join counts, and I'll elaborate in a second. And so the movement from the global statistic to a local statistic leads to a local join count statistic. And then I'll talk about a variant where we actually start with a continuously distributed variable, but convert it to a discrete one by means of what I call a Quantile LISA statistic. And then finally, I discuss some multivariate extensions of the local join count statistic. So in classic spatial autocorrelation analysis, so far we've dealt with continuous variables, but what if the variable is binary? So it takes on two values, 1 or 0. In the classic work of Cliff and Ord on spatial autocorrelation, a statistic called the join count statistic was presented. And the terminology has values of 1 as B for black, 0 as W for white. That's, of course, totally arbitrary. You could call it red and brown or anything you want, as long as there's only two possible values. Now, the principle of the join count statistic is very simple. You find out for every border, every join between two observations I and j, what is the layout of the variable of the values on both sides of the join? Is it 1 and 1, 0 and 0, or 1, 0, 0, 1? Right? That's the idea. And the statistic, the join count statistic, counts the joins. So counts for the data set how many of these are BB, WW, that's positive spatial autocorrelation, similar values in adjoining locations, and then the 0, 1s, the BWs, the negative spatial autocorrelation. Obviously, the set of joins, BB, WW, WB, or BW, exhausts all the possible number of connections, and since everything is done twice, it is typically divided by 2. So for inference, and this is what GeoDa implements, it's always easier to take the one case as the smallest case. Now, obviously, what is 1 and 0 is totally arbitrary, so you can always switch it around if it is not in the setup that you like. So the smallest proportion, less than half, becomes 1, the rest becomes 0. And we're particularly interested in coincidences of 1s. Obviously, we don't care about the 0s in this particular context. The classic join count statistic, as I mentioned, described in the book by Cliff and Ord from 1973, counts the numbers of joins, the number of situations where there's a common border, and it looks at the values on both sides. And the global BB join count statistic counts the number of joins where a 1 is next to a 1. Now, how can we express that mathematically? Well, first of all, we have our double sum again for all the possible pairs. And here we have a product of binary weights, 1 or 0, not the row standardized weights in this case, x at I and x at j. So 1 is this join counted. It is counted when all three of these elements in the product are 1. When any one of these is 0, it is not counted. Counted in the sense of this double sum here. This counts the number of times an x at I is 1 and has a neighbor, wij1, where x at j is 1. So there's 3 ones here, one for the neighbor relation, one for x at I, one for x at j. And so this is the BB joint count statistic. You can then figure out either analytically or by random permutation whether or not this is significant in the usual way. We won't dwell on that because we want to think about a local statistic. And if you recall my discussion of what is a local statistic, anytime you can write a statistic as this double sum, then the local part is the part that pertains to each individual xi location. Okay. So this local joint count statistic, we revisited. Actually, it was suggested a long time ago in the initial discussion of LISAs, but we reformulated it because, as it turns out, and this is something that was not obvious in the beginning, the local version is very obvious. I mean, we've already seen this. This looks exactly like a local Moran statistic. The only difference is that here the x at I and x at j only are 1 or 0, and the weights are not row standardized. They're in their original binary form. So what does this do? If there is a 1 at location I, then it counts the number of neighbors that also have a 1 at their location j. For a location that doesn't have a 1, the local joint count statistic doesn't make any sense because it's always going to be 0. And so that's the main difference between the local joint count statistic as presented here and some other similar statistics. These statistics came actually out of, a lot of them came out of point pattern analysis, and particularly there's a version in point pattern analysis. One of the most common statistics is the so-called K function, and there's a local K statistic that Art Geddes proposed in 1984, which is very similar in spirit in that for any given point, it counts the number of points in points being events in a given radius. So if you think of your spatial weights matrix as being a distance band matrix, then this local joint count statistic for any point, xi is 1, counts the number of points, xj is 1, in the distance band in the surrounding location. So formally, the idea is exactly the same. There's one major, huge difference in that, as we've seen very early on, briefly discussed, in point pattern analysis, the events themselves are random. So we only have, if you wish, the locations where something did happen, where an event did happen. We don't have the locations for the zeros. We don't have the locations where something might have happened, but it didn't. And that's the contrast with a lattice framework, which is what our discussion these past few weeks has been in that context. In the lattice frameworks, you have everything. You have all the locations, the ones with a 1 as well as the ones with a 0. That's a major difference. Another similarity is with a case control setup. Case control is basically where you have an event, say a polluting factory, and then you count how many things happen around that. And in particularly case control setup, the controls are locations that supposedly have nothing to do with the phenomenon that is of interest. And so they're supposed to reflect the population at large. It gets a little technical, but if you're interested, you can check out the references and read about this. It's similar, it's not the same. But interestingly, we discussed a couple of weeks ago the local G statistic, and specifically the GI statistic, which, if you recall, is a sum in the numerator, a sum over J of Wij Zj, which is again exactly the same thing as the local joint count statistic, with one big distinction in that the local GI statistic would count this both for locations with ones and for locations with zeros. So actually, this is how I came to this particular statistic. I was doing an analysis, and it had to do with different zoning categories and the extent to which they, clustered. And I thought, the statistic of choice would be the local GI. And then the results didn't seem quite right. And then I realized the reason they weren't right is because this statistic was computed for locations with ones and locations with zeros. Remember, in our discussion of the local GI statistic, it's a donut, but it doesn't look at the core of the donut, in contrast to, say, Moran's I, which multiplies z at I with that same expression for the spatial lag. So one way to think about the local joint count statistic is as a constrained version of the local GI statistic. Constrained in the sense that it only is applied to those locations where x at I is a 1 and the zeros are ignored. Okay, the interpretation is actually quite tricky because you have to think about what is going on here. We have, first of all, it only works, as I mentioned a couple of times now, it only works for locations where you have something, an event, let's call it, right? And then you're interested in finding out, is this event surrounded by other events like it, more so than would be the case under randomness? So we are looking for clusters of events. And in contrast to the point pattern setup, we observe both the events and the non-events. And the tricky part will be, given that we have the sum of events and the neighbors, is this something that could have occurred under spatial randomness or is somehow special or interesting, right? It's always the same kind of logic. So how do we get the inference? There's an easy way and there's a hard way. The easy way cheats a little bit because it says, given that you have a 1, and of course it ignores the probability of getting a 1, which to do it right, you would have to take into account. But then the number of neighbors that surround it is actually from a hypergeometric distribution, which is straightforward to calculate. But it is overly optimistic because it ignores the uncertainty with having the 1 there. So we kind of sidestep this. And as you should know by now, my preferred approach is not to get too involved in these analytical derivations where you have to make all kinds of simplifying assumptions that may or may not be realistic, but we just use the computational power. We have our value at the location, and we take the ones that are remaining and reshuffle them and then figure out how rare this is. So it's actually a very straightforward principle. It's an alternative to point pattern analysis in cases where you do have both the ones and the zeros, which unfortunately is not often the case. But in this particular example, and this is a real study, it was the case. So we have a map. This is for 2013 in the city of Detroit. We have some almost 385,000 parcels. Those are our observations. And of those 385,000, there were almost 6,000 sales. So clearly, if xi equal 1 means there was a sale at the parcel, that is going to be a small fraction of the total number of parcels. So our interest is in finding out hot market areas, finding out places where sales are surrounded by other sales, more so than would be the case under randomness. So how do we do that? So first of all, we all these little circles are the parcels. The black dots and the red dots are parcels with sales. The red dots are parcels with sales that also have sales in a KNN with 30 nearest neighbors surrounding, which basically corresponds to a little more than a block for Detroit. So here, for example, we have 2 sales or more sales that have nothing going on in the surroundings, whereas, say, here, this bunch of red dots, they all have sales in their surroundings. So what we're trying to find is, of these red dots, are there configurations, are there groupings that are, in a sense, more clustered than they would be randomly. And in this particular case, it's important to keep in mind that the neighbors are not just the other colored dots, but they include all the uncolored dots, all the parcels that did not have a sale. So we do our thing, we compute the local joint count statistic, we do the permutations. We want, as I said, we want to find the cases where the number of neighbors with sales is larger than randomness. So we do our thing, we find these hotspots. Obviously, this is a case of a bad map. If you recall my early discussion of some of the bad maps, the dot maps are notoriously potentially misleading because the size of the dot has to do with the scale of the map, and so these dots are way too big, and we can actually see what's going on when we zoom in. And this is an example of our types of results. We find in this is for the whole data set, we have 38 locations that have more neighbors with sales than would be the case under randomness at a p-value of 0.001. So this is one way. It's actually an unusual example because oftentimes you only have the sales data. We were able to apply this principle to Detroit because we had a parcel map with every single parcel in Detroit. So that is an unusual situation. But the local joint count statistic, very simple principle, only for locations that have an event, count the number of neighbors that also have the event, and then check out whether that is rare or not in some sense. So this is the principle to deal with discrete or binary, to be specific, binary variables of interest. Now, with the Quantile LISA, we kind of use the same idea, but in an indirect way. And there's a whole literature in statistics and econometrics on quantile statistics. And the reason for that is to go away from the traditional focus on the full distribution of a continuous variable. So we're back with continuous variables, but what we're going to do is convert that continuous variable into a discrete variable and then apply the local joint count to the discrete variable. So it's kind of an indirect way to get to the local joint count statistic. And the literature on quantile regression in econometrics and statistics is quite large. The main motivation is to come up with some more robust and in some cases some more interesting interpretations of the regression result. In a regression, traditional ordinary least squares regression, the focus is on finding out the conditional mean, the predicted mean given the values on the right-hand side. And instead, one could focus on the median, which is often more robust to outliers, but also to particular percentiles, like the top 10 or the bottom 10. This turns out to be extremely interesting in financial econometrics, where you're typically not interested in the middle, but you're interested in the tails of the distribution where the crazy stuff happens, and understanding that is one of the motivations behind quantile regression. So how does this work? In my approach, it's actually much simpler than in the regression approach. Think of a variable with a continuous distribution, f of I, and we're going to sort the observations from small to large, and then we're going to pick a particular quantile. Now, I just call it Quantile LISA because that sounds good, and that's also the main application, but it doesn't have to be a quantile. It could be any interval that is of particular interest. And so the key notion is, and it's very simple, for those observations that meet the interval, that fall in the particular quantile, you create a new discrete variable that takes the value of 1. All the other observations get a value of 0. So this is how we go from our original continuous distribution for a variable to a discrete distribution where we now have zeros and ones. And then, of course, we're in business, because once you have reduced this continuous distribution to a particular quantile, the quantile becomes the binary variable, and we can apply the local joint count statistic. This is what I call a Quantile LISA, Quantile Local Spatial Autocorrelation. It turns out to be particularly effective to focus on the extremes in a distribution. And if you recall, both Moran-Xi and local Geary, local Moran-Xi and local Geary, consider the whole distribution. So they have both high, low, and things that are similar, sometimes in the middle with local Geary. So what we do here is we say we don't want all this information. We just want to find out, are the extremes in this distribution somehow clustered? And you can think of it as another take on the box map and the box plot. If you recall earlier on in our exploratory EDA ventures, we had a box map that showed outliers on the map. Now the question is, okay, good, we have these outliers. Are these somehow more grouped together than they would be randomly? That's our research question. We're interested in extreme values at the upper end or at the lower end. And so we're purposely discarding a lot of information because we don't care about that information. We only care about the extremes. We don't care about the rest of the distribution. So all of that becomes 0 in the local joint count terminology. And as it turns out, in practice, I've found this to be very effective at bringing out interesting patterns. So I have an illustration here. This is a map of 971 census tracts for Chicago. It's a quintile map, so every category has about 20% of the data, 158 observations. We are interested in the extent to which the top quintile clusters more than would be the case under spatial randomness. Always keep in mind, what is the point of departure? The point of departure is spatial randomness, which means no rhyme or reason in this map, no structure whatsoever. Now we see this kind of dark colored group and this kind of dark colored group and then another group down here. Our question is, to what extent is this grouping likely under spatial randomness, or is so different that it warrants further investigation? And so here's the result. This is the top quintile. We have our 158 observations. The rest we don't care about. Now, we know right off the bat that locations like this one and this one, we don't have to concern ourselves with, because it's not the location that matters. It's whether this location is surrounded by other locations like it. And clearly, this is not the case. Now here it's different. Here we have several locations, several blues that are surrounded with other blues, similarly here and similarly there. So then, after we apply the local joint count statistic to this phenomena, we find a strong cluster in this particular area and another strong cluster in this particular area. So what this does actually is sharpen the insight at the extremes. And to illustrate this in yet a slightly different way, so when we do our local Moran statistic for this particular variable, we have high clusters, and they're essentially in the same locations. But these are the significant high clusters. And one of my pet peeves, and I think I mentioned this a number of times, is that oftentimes this high is not interpreted properly. It really should be interpreted relative to the mean. And it's not necessarily that high if it's this close to the mean, for example. So what the Quantile LISA does, it takes the top 20%, the top quintile, and in essence, it cuts off all of these observations that are closer to the mean and ends up only with observations that can be considered to be more extreme. Remember, this is one standard deviation, so all the ones that are within one standard deviation from the mean are removed by focusing only on the top quintile. So to me, that is a very efficient way to kind of focus on what really matters at the extremes of the distribution. And just to put things a little bit into perspective, here's a comparison of the results of the local Moran I. Here on the left, we see high here, high there, low over here. Local Geary, high, slightly different setup. This is similar to local Moran, but much larger. And then the low is much more disconnected than it is for the local Moran. And then in the Quantile LISA, we pick up this cluster here, which is similar to these two. And then we pick up a strong cluster in this location, which is not really evidenced by the local Geary, but is picked up by the local Moran. So here again, you know where I'm coming from. Different ways to look at the data. What do they each bring out? And then maybe you can find something interesting that deserves to be drilled down further, need to be focused on some more. Okay, just like we generalized the local Geary to a multivariate setting, we can generalize the local joint counts to a multivariate setting. But there's an important distinction. So we have two types. Let's just take the bivariate case first. We have two types of events, event X and event Z. And so you have to think about what these events could be and whether they could coexist at the same location. For example, if you have multiple time, you have block data, and you give a block a 1 if a particular type of crime has occurred in that block. So if you have, say, assaults and vehicle break-ins, those are two sets of events. You know, in point pattern analysis, you can make a map of these points and then do your statistics. Here we have every block. So every block either has a 1 or a 0 for assaults and vehicle break-ins. But there's no reason that you couldn't have both an assault or a vehicle break-in in the same location. So that's what I call co-location. Xi equal 1, then it's possible to also have Zi equal 1. In another case where you have exclusive categories, so something either is or it isn't, for two different things. So for example, we have two zoning categories. A single block or a single parcel can only have one category and can't have both. A case control situation, you either are a case or a control. You can't have both at the same location. So that I call no co-location. And no co-location means if X is 1, then Z has to be 0. If Z is 1, then X has to be 0. So that's a different situation. And each of these situations will have its own multivariate extension of a local joint count statistic. So let's first look at the no co-location situation. And obviously this only works for two variables, since for three variables you would have contradictions built in. So for two variables, That's why it's called bivariate local joint count. That's specific in GeoDa, deals with this situation. So in general, to have a no colocation means that if you have xi 1, in order for it to count, you have to make sure that the second part is also 1. And since there's no colocation, zi will be 0. And since zi is 0, this product is 1. And we're counting the situations where x at I is surrounded by z's at j. So because x and z cannot coexist, so the only way you're going to have a z at j that is 1 is if x at j is 0. So we present this this way as a product to keep the generality and to show how it is bivariate. But for all practical purposes, in the first part, zi will be 0, so we just have xi. In the second part, xj will be 0, so we just have the zj's. So what does this bivariate local joint count statistic do? In the same spirit as before, for those locations where x at I is 1, we count the number of neighbors, but now the number of neighbors where z is 1. And so again, the statistic is really the second part, but it's only applied for locations where there is an event. So if there is an event of one kind, we count the number of events of the other kind that surround it. So this, if you wish, a sort of notion of negative spatial autocorrelation in some sense. The inference, same as before, but now we have to be a little bit careful in that, again, just as we did with the multivariate local Geary, we shuffle around the tuple. So we shuffle around the existing pairs of 1s and 0s, or 1s and 1s, or 0s and 0s. That's we shuffle around, and then for each instance where we have a 1, we count the number of z's. A 1 for x, we count the number of z's that are 1 in the surrounding case. And obviously x and z can be switched, but there, first of all, it's not a symmetric relationship, but also you have to make sure that you keep the scarce, the smallest proportion for the neighbors, otherwise the p-values don't make sense. So that's something to keep in mind. This is kind of a niche interest in my work. Doesn't happen very often. The more common situation is the colocation local joint count statistic, which is a multivariate extension. And colocation means that two events can colocate. And what's important to keep in mind, especially if you've done some work in data mining, just finding collocations is often of interest in and of itself. But here we go a little further. So we're not only interested in finding those observations, those locations where both events happened. In marketing, you know, if you buy a beer, do you also buy potato chips or whatever? If you buy a soft drink, do you also buy potato chips? Those are the types of things in data mining one is interested in. And are these things coexisting? Here is a little bit more, because it's not just do they co-locate, but are they surrounded by other locations where we also have co-location? So we have event X and Z happening at a location. Is that combination of X and Z replicated for the neighbors, or are the neighbors just some random mix of 1s and 0s of X and Z? That is really our interest. So again, is this notion of cluster that is more than one observation, but it's one observation with its neighbors. And the math is very simple. If we have X and Z equal 1, then this product will obviously be 1. And then we just count for the neighbors, again, binary weights, those instances where for the neighbors x and z are both 1 as well. And that's a very simple extension of the local joint count. And then this can be extended to multivariate setting very easily because it's just more products of values that should all be 1 together. Now, one drawback, cursive dimensionality, is that once you do this for too many variables, first of all, you won't have very many collocations. They become extremely scarce, but then having collocations surrounded by other collocations becomes even more scarce. So at some point, it becomes not that meaningful because the number of locations where you have 1 in this first term becomes so small that it's almost not worth looking for clusters, because if you have a collocation, that in and of itself is of interest. And when you have many variables, this will very quickly happen. And I'll illustrate that. And in fact, I've illustrated it in the lab notes also, how rare this is. So same thing as always, conditional permutation of the tuples, and we count how often this happens under spatial randomness, and we compare whether this is rare or not. So that's we're really looking for clusters of coincidence of multiple events. So not just in a location, but surrounded by other locations that are the same. Okay, since we can do this for the joint count statistic, we can also do this for our Quantile LISA. And it's just a simple extension of the notion of a bivariate or multivariate local joint count statistic. And we can do this for different variables between, say, their top quintiles. To what extent not only are the top quintiles co-located, but are they surrounded by other locations that are also in the top quintile, and how rare is that? That's a measure of positive spatial autocorrelation, if you wish. But then we can also apply it between quantiles of the same variable, let's say the top and the bottom. To what extent are the top values surrounded by bottom values, or the bottom values surrounded by top values? This is an extreme notion of a spatial outlier, where we only focus again on the extremes in the distribution and forget about the middle part. So this would be a way, an alternative way to look at negative spatial autocorrelation. So multiple variables, there's typically the same quantile in multiple variables, that's positive spatial autocorrelation. The same variable but two different quantiles, typically top and bottom, that's negative spatial autocorrelation. But again, this only works for two variables. The no collocation situation does not extend to more than two variables. And to illustrate this, we're going back to our Chicago example. We already saw this map, the premature mortality. Now we're superimposing a quintile map of percent uninsured. So we're not only interested in where are these quintiles and to what extent do they coincide, but also to what extent are those locations that do coincide surrounded by other locations that also coincide. That's a much stricter or tighter, if you wish, notion of what is a meaningful location, what is an interesting observation. So the first step in this is we put these two on top of each other. We've seen how to do that with our collocation map in GeoDa, and right off the bat, we started with something like 158 quintiles top for each, and 26 of these are collocation. Now, in some contexts, as I mentioned, in data mining, this would be enough. These are places where you have both events happening in the same location. But from our perspective, this is not enough. What we're interested in is finding out, are there situations where these are also surrounded by other collocation instances? So as before, clearly, when it's just one observation, this is not going to happen. I mean, there's nothing meaningful surrounding it. But here we have these groupings, both here and here, of multiple census tracts that have collocation and also collocation for their neighbors. So then the question is this something that is likely under spatial randomness, or is it highly unlikely? And we do our same thing. We do our conditional permutation, and then we find this map where we find, so this whole part, forget it. So these are several neighboring locations. They're not interesting enough. Same with these or these, but the interest is there in that location right here. And specifically, we find that 3 locations are very significant. So their particular layout, and obviously they're neighbors of each other, so this is going to help forming a cluster, and this is very unlikely to be due to chance. So that in contrast, you may not appreciate this at this point, but so far the tendency of the local statistics, especially the multivariate ones, the multivariate Geary in particular, is to find a lot of supposedly significant locations. Here, in a way, it's the opposite. You get very few. But then that makes them more interesting, I should say. And for those of you who are in Hyde Park and know the area, you will not be surprised that these are actually our neighbors across from the interstate in West Englewood, where we have coincidence of these 2 situations, the increased mortality and the lack of insurance. So then the final example is the negative spatial autocorrelation. And here I bring up yet another map with health information, health literacy. So dark is high literacy of health, and light is low literacy of health. And the reason I bring up this particular example is that unlike a lot of the previous maps where we saw groupings of similar observations, so they tended to be dominated by clusters, this particular one has a lot of spatial outliers. So first analysis is a local Moran, and you see these high-low outliers, and then the low-high outliers. Many more, 9 in this case, than you typically see in your standard analysis. So that piqued my interest to see, well, what if we take a more extreme view, and to what extent are these high lows and low highs things that are happening near the intersection of the axes in the Moran's eye, in a Moran scatter plot, but to what extent are they really extremes being next to each other, which would be real spatial outliers. And so the way we go about this is we again create 2 binary variables, 2 0 1 variables, one for the top quintile and one for the bottom quintile. So we have 158 for each. Now, in this case, clearly you cannot have collocation because you cannot be both in the top or in the bottom quintile, but we have an interesting notion of negative spatial autocorrelation of spatial outliers. And so we do our thing, we apply the bivariate local joint count. We can do it for either one of these because they're both rare, so we can have both low-high and high-low locations. And we see we cut it down to 4 in the one case and to 2 in the other case. And these are places, but the p-values are very weak. But these are places where there is extreme juxtaposition of a top quintile tract surrounded by more bottom quintile tracts than would be the case randomly, or vice versa, a bottom quintile tract surrounded by more top quintile tracts than would be the case under randomness. So the bottom line for this Quantile LISA, and this is something, I mean, as I mentioned, it's very recent, but it's something I've come to like quite a bit, because the other statistics, and this is in the spirit of quantile analysis in general, the other statistics can muddle things a little bit, especially around the middle, around the mean. But this just cuts to the chase. It says extremes. How are these extremes co-located and also surrounded by other co-located extremes? Or opposites. What are the extreme opposites? There's not that much loss of information, as we saw in the one case in comparing to the results of Moran-Zai and Giri-C. But I personally find it a very effective way if you're interested in the extremes of the distribution. So this concludes the set. So today we went beyond continuous variables and broached the topic of discrete variables, and we saw this new statistic, a local joint count statistic, with both univariate cases and bivariate and multivariate extensions, and then a kind of an indirect way of getting at discrete variables where we turn a continuous distribution into quantiles and then deal with the quantiles as discrete variables. So you should now have a set of tools to explore interesting patterns in data distributions. But remember, the fundamental notion in exploratory spatial data analysis is you discover interesting patterns. There's no processes, there's no causation. For that, you need actual models, which is the topic of a different course. Good luck with your project, and I'll see you maybe in another course. Bye-bye.